This is lecture 21, chapter 6. In this lecture, we're going to continue talking about trusses and introduce the concept of zero force members. So up to this point, we've solved trusses using method of joints, and we're going to talk about zero force members in the context of trusses. And I'm going to do one more example of method of joints. In the next lecture following this, lecture 22, we'll learn how to do method of sections. Neither of which is particularly different, but just one is a little more useful in certain situations than the other. So zero force members come from the idea, and they're not really truly zero force members because we use this terminology, but nothing has zero mass, so therefore there's always going to be a load of gravity on any member. It's just that the idea is that within a truss, the weight of the member itself compared to the loads that it carries is so much smaller that we can essentially assume it to be zero relative to those. That's why we don't account for that weight when we do our calculations. Same is held in this case is that if in certain loading situations of a truss, there may be cases where a particular member carries no load in that configuration. But of course, if the loading changes, then that member that was previously zero may become active. And that's a common question is if there's zero force members, why are they in there? And that's the answer, because the loading obviously is a dynamic system, not a static system. So we can determine zero force members by what is called inspection. And the idea of inspection is by looking at the way that the members are configured in the truss and relative to the forces that are applied at the different joints. So two of the rules that we're going to use, and I'm going to say them, then I'm going to show them to you on paper. But the first one is if you have two non-collinear members, which is just a fancy way of saying not straight, two non-collinear members connected at a joint, then both are zero force. And so that comes from the idea that if you have two members meeting at a point, if they're not equal and opposite to one another, then they can't be zero force because we know that all of our members are two force members. The second point is if three members are at a joint and two are collinear or straight, then the third is a zero force. And this comes from the idea that if you have two meeting together in a straight line, they're going to be equal and opposite, and whatever that third one is can't be supported, and so therefore it's zero. Now, this assumes in this case is that this only applies to when you have no externally applied load at that joint and you don't have a reaction or a support. So this is generally within the frame of the truss. Now, what this means physically is if we were to draw a simple truss, let's say it looked like this. And let's say in this truss, we support it here, and we support it here, and we apply a load here, and maybe we apply a load there, and maybe we apply a load here. So if we think about it, this member here carries a load that's either going to go that way or that way. This member here carries a load that goes that way or that way. So when it gets to this point here, there's nothing really to oppose this direction. Now, this isn't the same as if we had a reaction here, because then the reaction would add a support to this and this. This is without a reaction. So what we've done is we've cantilevered this off the end. And so because neither of these members has an opposing member to support it, then both are zero force. So in effect, you could cut them off and the truss would be no different. Now, if we were to say add a member, let's say, or add a force, let's say we applied a force like that, then this would no longer be zero force, but this would be. Same is true as if we were to get rid of this, and apply one like that. Therefore, that would oppose that, and this would be the zero force. So that's the idea with two. It's not as common as the second type. Now, the second type deals with when you have a truss. Let's say you have, we could even look at the same truss here. And actually, this one's not going to work. Let's do something a little different. There we go. So something like that, not very pretty, but if we support this truss here and here, then if we look at this is fine, it has an external reaction, but let's look at this here. If we have something like that, then we know that this is going to be opposed by this member, but this joint here has nothing to oppose this member. So in effect, this disappears. Same on this side, because there's nothing to oppose this direction. This will have to go to zero also. Sometimes you may have something that looks like this, and there'll be one member like that. So it doesn't necessarily have to be normal to it. It doesn't have to be 90 degrees. It could be any angle. But anytime you have a line like that where there's another truss, another member intersecting, this one has to be zero force. Now, if we apply a force here, then this is still active. Then that changes. But again, this is criteria with no external force. If you have something like this, then all three are non-collinear, meaning no two are straight. Therefore, all three could potentially hold a load. And if you have more than three, if you have four, then you can't tell just by looking at it. And so the way this works is that you may find through calculation that in this case, for example, this may be zero, but you can't just look at it and know a priori that it is. So go back. So let's look at an example. So in this one, so if you had a chance to download the worksheet for this lecture, and it has on it these several trusses. So we're going to go through 3 different trusses at this point and talk about zero force. Now, if you look at it, what I would do at this point is I would pause the video and pick out all the zero force members you think you see, and then compare to what I have. So now you're back, you started again, and let's look at this. So first one I see is over here, BC. Notice how that A, B, D are equal and opposite. That's going to make that disappear. So BC is now gone, all right? But notice how now that BC is gone, CD is now zero. And so because this is now has 2 collinear with 1 non, then this one has to disappear. Now, the fact that the other end has 1, 2, 3, 4, 5 doesn't matter. It has to follow the rules on both ends. And so there's my arrow pointing, and my one is BC. Kind of got ahead of myself. So the next one, we have CD or DC, however you want to call it, that drops off. And then we go on to the rest of them. Well, it looks like none of the other ones meet the criteria. FG would, except that you have a load on it, so that doesn't count. But if we go over to the other side, you notice that JI is missing, or it doesn't support, because here you can see it, there's a straight line, but because there's nothing to oppose it, it can't support any load. And you could work this out. If I gave you a value for P and Q, and you worked this out doing method of sections, it would work out. You'd notice that when you came to this joint F, and you tried, no, I'm sorry, not that joint, you came to this joint G and you tried to calculate it, it would come out to be zero. So there's nothing magic about this process. It just allows you to pick things out without having to calculate them. So that's rid of that. And now we have IJ, but because we got rid of that, now IL has to go because it no longer has anything. And now you're probably seeing a pattern. And if you look down, you'll see that the next one is going to be down at NM. And so NM's gone, and that means that ML has to disappear too. And so that's all our zero force members. So hopefully you saw those. You may not have seen every one of them, but at least hopefully you saw a few. All right, so let's look at this one now. So this one is a little trickier because it kind of defies what you would think should happen in this type of system. Now remember again that when you're looking at this truss, you only have vertical forces. There are no horizontal forces. So it's safe to say that the reaction at F in the X direction is 0. So if that's the case, then FG probably can't really be there. And so that's probably going to drop out, but let's look. So first thing we have is, I'm going to say is DG. I did this a little differently than the other one, but here's DG. That disappeared because that was the most obvious one. But notice how once it drops out, that because there's no FX, that means FG has to drop out, which also means that GH has to drop out. Here we get that. And I left the G kind of floating there because you wouldn't physically remove the member. This is just for illustrative purposes. But you can see that the truss is still statically stable with this because F is supported at A. And since there's no lateral force on it, we don't have to worry about it tipping over. But we can't guarantee that's always the case. So we got rid of those. And so the same can be held true now if we go up to DB. So notice that DB is now going to disappear because it is two straight lines and the third being non-collinear. And then we have not lastly, but we have the JI dropping off. And so IJ drops off. And then you have to ask yourself, is there anything else? And I think that's it, because the other ones all have forces attached to them. And the IJ, again, can't exist because there is no X force. So hopefully that makes sense. And, oh, yes, one thing, I kind of got ahead of myself. HI also disappears. And that makes sense because HI disappears because you don't need that cross member there either because there's no X force. So these can be tricky. Typically, I will on an exam or a quiz, I'll give you a truss, and then you pick out the zero force members, and that'll be like a secondary part to the problem, or maybe you're finding some of the values of the forces. But again, if you follow these rules and you see the practicality of it or the way it works, it will solidify after you do a few examples, because you can see that HI can't exist, or it can't support a load because there's no X. And so there's nothing there, it's just kind of sitting there. All right, let's look at this one now. Now this one starts up in the corner at A. Notice how P is coming straight down at A. So that means that AC is not, there's no lateral force again on this truss. So AC is effectively not needed. And then if we look at, we keep going, we notice that now CE has become an odd one out. So it's going to disappear. And then if we come down to E, we see that E is now no longer needed because it's no longer, it's part of a 3, with the third one being not straight. And then that gets rid of the last one, FG. And there you have it. And so now everything's supported, it's still there, and So, but we have identified our zero force members, and that's that. So hopefully that makes sense. There are examples in the homework you can look at, but I think after you look at a few, the idea becomes pretty clear. Now in this one, I don't know if I'll do the whole everything for it, because actually the problem isn't to find it, in the problem you can find everyone in it, but I'm not going to do that, but I'm going to do a few of them, and if you choose to continue and try to find it, you can. It looks more intimidating than it is. For one thing, if you look to the right side of the truss, you notice that KJ is a zero force member, which means that IJ is a zero force member, which means that IH is a zero force member. So as a result, if you find GI, IK, and KL are going to be the same value as our LJ and JH are going to be the same. Now, this is not a symmetrical truss because the loading is heavily weighted on the left side, not on the right. So you can't use really any of the information from the left or the right, but because those internal members are zero force, it does make the calculation quite easy. So let's do a few of those just to show another example of this type of truss. This should get you well prepared to do the homework. So here's my truss. It's an exaggerated way I've drawn it. But one of the things to notice with these arms, especially if you look back at the drawing, is that this here is a 45-degree angle because it rises 2 and goes over 2. So that's a right triangle. And this is a little different. This is going to be, it's going to rise 1 and run 2. So it's over root 5. So we're going to use that in our calculations. Now, when we look at this truss, we can find AY by summing the moments about L. And that's an easy process. I'm not going to do it for you, but if you do that, you find that 4.5 kilonewtons a day. And so out of a total of 5, that means you only have 0.5 on the other side. So the majority of the load is on at A. Now, if we look at joint A and draw it, we can see that we have AB, we have AC, we have a 1 kilonewton force down, 4.5 coming up. And I've guessed that both of them are in tension, and realistically that can't be the case. One's going to be in compression, but this will give us a chance to show again how you deal with that. So I'm going to guess them both in tension. So that means if I sum my forces in the X, now in this case, making a triangle like we did a proportional triangle, you could do it just like we did before. It's not as clean as it is when it's a nice 90 degree. So I'm just going to go ahead and sum my forces. So summing force the X, I know that I have 1 over root 2, so that's the X component of AB, plus 2 over root 5, that's my exponent of AC, that all equals 0. You call that equation 1. Then I'm going to come down, sum the forces in the Y, 1 over root 2 AB, plus 1 over root 5 AC, plus 4.5 minus 1 equals 0. So I'm going to take this equation, I'm going to multiply it through by a negative 1. And you can probably see why I'm doing that because I want to get rid of one of my terms. So that becomes negative, negative, and negative 3.5. So if I come back and I put equation 1 in here, then I have negative, positive, those drop out, and I end up with 1 over root 5 when I add the negative to the positive. AC equals 3.5, gives me AC equals 7.83 kilonewtons in tension. So my answer is correct. I guessed correctly on AC. It is going the tension direction. And so now I can just take that value and I can plug it back in here. It's probably the easiest. And if I do that, I can see right away that if I have a positive and a positive, that's not going to be 0. So AB is obviously going to come out negative. And when I do that problem, I end up with AB being equal to negative 9.90 kilonewtons, or another way, it's 9.90 kilonewtons. And that's a compression. So that's that first joint. And so as you get familiar with these, you'll do more and more, and they'll become more familiar, and you'll be able to see right away, and probably be able to guess more correctly, or not more correctly, but have a better sense of which direction they're going to go in. So let's go ahead and do joint B. I'm going to go ahead and pause and draw that for you. So now we're going to look at joint B right here. We've got AB and AC. Now, one thing, when we come to AB, we note that we know this one, but we have 1, 2, 3 unknowns. So that would work. However, if you've probably noticed already that we could have gone to C, in which case we have 3. But notice what C is. If I have AC going that way, then CE is opposing it. Therefore, this is also a zero force member, which I didn't mention earlier because I wanted to play out in the problem. But because that disappears, it makes this solvable. So if we come up to that, we have something like this. So we know, sorry, I just want to show that a little bit. So we know that it's still a 1, 1 root 2 on the 45 degree. We can essentially erase BC, leave it there. And so I'm assuming in this case BD is in compression, BE is in tension. I'm going to sum the forces in the Y. 1 over root 2 AB minus 1 over root 2 BD minus 2. And because I only have one unknown, I can just solve directly since B is a horizontal force. So 9.9 for AB plugged in there minus that equals 2. I get BD equal to 7.07 kilonewtons, and that's it, compression. So then I do the same thing with this. I sum the forces in the X, and if I do that, I have BE positive plus 1 over root 2 AB minus 1 over root 2 BD. But I can kind of see where this is going because this is a bigger number than that. And so if that's positive, there's no way this is going to add to 0. So I end up coming up with BD equals a negative 2, or BD is 2.00 kilonewtons in compression. So I was wrong. It goes the other way. So you don't have to change it in your work, but you just want to note that when you go on to the next joint so that you have the correct orientation. So that's that. So if we go back to our diagram, so we have this, determine that, determine that, determine that. So the next step is, if we go up to here, we have 1, 2, 3 unknowns. So that wouldn't work too well because if that's for self, it's this and this is definitely not a zero force member because this exists. So instead of going to D where we can't do anything, we're going to go to E. And this is why you have to start with method of joints at a corner, because if you start inside the truss, it's not going to work very well because you'll have too many unknowns. You'll set up your equations, but you won't be able to solve anything. So I'm going to go ahead and go over to E now, and we'll draw joint E and see what that looks like. Pause while I take care of that. Okay, so let's continue now. One thing I realized is I did write BD down here. I don't know why I was looking at this, so I meant to write BE because we already solved for BD. BD was 7.07, so it came down here, just a little note, in case you didn't catch that. One other thing I mentioned earlier, and that was intentional, was if we look at this, I said that, well, if you go to E, you can't solve it. You have to go, or you can't go to D. You have 1, 2, 3, 4 unknowns. And that was true. When you come to E, though, notice how we hadn't solved for CE yet. So we had BE, CE, and so out of these four, we only knew one group. So that appeared to have three unknowns. And what I didn't mention is that because that's a zero force member, we know that AC is equal to CE. And hopefully you already saw that. If you did, that's good. That means that you're understanding this really well. And so because we have CE, that's 7.83 as we found earlier. AC 7.3 CE, so that means we only have those two unknowns to contend with. So I'll never give you a problem that's statically indeterminate that you can't solve. So if that's the case, just make sure that you're paying attention to everything that's going on. So in this case, again, like I said, CE we know, 7.83 in tension, and EG we don't know, and DE we don't know. So we're going to guess they're both in tension. We don't know that. We know BE is in compression. So if we go ahead and sum our forces in the X, we get 2 root 5, because now we're on the lower leg, which is the 1, 2 root 5 triangle, EG minus 2 root 5 CE plus BE. And so if we go ahead and solve for that, we see that we can 2 over root 5, we move this to the other side, and then solve for EG, multiply both sides by root 5 over 2, and then plug in the respective values for CE and DE here. And that gives us a value of EG of 5.59 kilonewtons in tension. So now we can go back and sum the forces in the Y, and that will allow us to find our DE value. So if I sum the forces in the Y to 0, I know that I have DE and minus 1 over root 5 of CE plus 1 over root 5 of EG. And that all equals 0. And so if I go ahead and I get DE is going to essentially equal 1 over root 5 CE minus EG. All right. And if I plug that in, that's 7.83 minus 5.59. So take the difference, multiply by that, and I get a DE value of 1.00. And it's positive, so I was guessing correctly. It's tension. And again, all in kilonewtons. Okay. So that pretty much tells us everything. We have this, this, this. We have BD. We have this, this, this. So really, we're just missing these other two. And if you want to go ahead and solve for those, you're welcome to try that if you want the extra practice. It turns out that if you go up to D, you can just do the same thing I did. This has changed slightly. This is now back to a 1, instead of being 1, 1, let's say 1, 2. So this is a 1, 2. So this line and that line have the same slope, and that's about the only difference. So if you want to go ahead and solve for it, DF ends up being 5.03 in compression. So let me write down there. So DF equals 5.03. That's kilonewtons, and that is in compression. And if you want to solve for DG, then that gives a value of 0.56 kilonewtons, or 560 newtons, and that's in tension. So those are the two final answers. And again, you could work your way all the way over. That's necessary at this point, but if you'd like. Now, once you have those two, you can solve for FG, FH, and then GH. And once you have this
then you can go down to H, solve HJ out through JI. Once you have G, you can get GI, which is going to be equal to IK and KL, and you'll have the whole truss. Now, that's a lot of work to do. That's why on the homework, I only give you a few of these because they are time consuming. And but once you do a few, you should have no problem. So hopefully that made sense. And so next lecture, we're going to talk about the method of sections. And just to give you a quick preview, the idea of the method of sections is that, let's say that we did want only to know FH and GH and GI. Well, what we could do in that case is we could just cut the truss. If we cut the truss, then all we're left with are these three disconnected members. And because we know equilibrium is in the rest of the truss, this rest is treated as a solid. So we don't need to worry about it because we know at each joint it has to be in equilibrium. So that's the idea with the method of sections. And so we'll do some examples of that and talk about that in the next lecture. All right. Thank you and have a good evening.